Okay, so good morning. So Olivier will continue his talk on Anosov representation. Yeah.
Thank you very much. So yesterday I finished with these examples of convex in the projective space with a compact action of a subgroup of linear transformation, and I claim they are Anosov in that sense. So if I put the group in this orthogonal group, then they become Anosov. And this representation of SL3 is just by conjugation on 3×3 matrices. And the trace is the quadratic form. So AB goes to a trace of A times B is a symmetric bilinear form of signature 6-3, I believe, on 3×3 matrices. But it's not a very nice way to phrase this condition. So I would like to express it more concretely, and it is valid for any subgroup of SL3, saying that tot gamma is Anosov means the following. There exist maps beta 1 and beta 2 from the boundary of the group to the projective space and to the dual projective space that I like to see as a Grassmannian of two planes in R3. Those maps are continuous and equivariant. And they satisfy a number of additional properties. The first is for every point in the boundary, the line beta 1 of eta is contained in the two plane beta 2 of eta. And for every pairs of distinct points, the line beta 1 of eta is in transverse position with the two plane beta 2 of eta prime. And the last condition are with respect to the dynamic of the action. So we request also that beta 1 and beta 2 are dynamic preserving. And finally, a growth on the eigenvalue that was property number 6, that mu1 minus mu2 goes to infinity when element of the group. Okay. So what do how do I get this map in this situation? I have an identification of boundary of the group with the boundary of omega, and this gives my map beta 1. And on every point, the boundary, I have a unique tangent line to this point. So this is a C1 character of this boundary. And this unique tangent line, I can see it as, it's a line in RP2, but I can see it as a plane in R3. And this gives the map beta 2, which is this obvious inclusion. And this property reflects the strict convexity of this set omega. Okay. And then you have to check those property, but maybe I want to relate the pair beta 1, beta 2 with beta, that was a map, the boundary of the group to the space or to the projective space of 3×3 matrices, which is the map that I need to have tau of gamma Anosov. And this goes like this. To a point eta, you associate a vector subspace of matrices. So all the matrices that satisfies the following properties. The image is contained in the line beta 1 of eta, and the kernel of the matrices contains beta 2 of eta. Okay. And you can, this is a one-dimensional subspace, and this establishes how to prove that this is Anosov. And you can also find beta 1 and beta 2 in terms of beta. So beta 1 is a common image of all the matrices that you have in this line of matrices. And beta 2 is a common kernel of all the matrices that you have here. Yes? Yes? So in the condition of the lemma, you mean? So there is a direct sum of a line and a two-plane. And well, I see element of the projective space, sometimes at point in the projective space, but sometimes at lines in the vector space. So this direction condition is a condition that is expressed in the vector space. Okay. And if you want to express it projectively, it means that the point beta 1 of eta doesn't belong to the line, the projective line that corresponds to beta 2 of eta prime. Okay, sorry about this. So the question is can I remove or not this condition for RP2? I have to think about it. I'm sure there are necessary and sufficient conditions. There are maybe not minimal conditions. Okay, so it's a good question. Good. So I would like to give 2 more examples and then go to geometric properties of Anosov representation. So the next example is related to Francois Guérito's first talk. So I take G, which is OP1, the orthogonal group, or the isometric group of the hyperbolic space. And I can see the product group G cross G either as a subgroup of O2P2 or as a subgroup or O P plus 1, P plus 1. You have a kind of freedom of how to normalize. I mean, it's just because OP1 is also isomorphic to O1P. So when you do the direct sum, you can choose the signs and one factor. Okay. And a subgroup gamma in G cross G is thought as a pair rho J of homomorphism from gamma to G. And I want to understand when the subgroup is Anosov in G prime. Okay, so the proposition is the following. I will say that rho J of gamma is Anosov in G prime. So if and only if the following happen, and of course I cannot distinguish the 2 factors of G in this product, so I have to allow exchanging the role of rho and J in this statement. So this is up. to exchanging rho and j. And so the condition is that j is Anosov and dominates the representation rho. Okay, so in Francois' talk there was pairs of representation like this. The J was not under such restrictive hypothesis. We just wanted a discrete subgroup in OP1, but there was this condition that there is a domination in the sense meaning that there is a equivalent contracting map from the hyperbolic space to the hyperbolic space. And the last examples that relate with surface group representation is what is now called Hitchin representations. Okay, so I start with a gamma, a co-compact lattice in Si2R. Maybe I had that gamma is torsion-free, but it's not entirely necessary. And I want to deform gamma into SLMR for m bigger than 3. And for this, I need to put first this gamma in SLMR, and this will be by an amending of SL2R in SLM. I denote tau m, which is the action of SL2R on a homogeneous polynomial of degree m-1 in two variables x and y. This is isomorphic to SLM. Okay, so this is my notation for the space of degree m-1 homogeneous polynomial the variable x and y. Okay, and the theorem is as follows and is due to Francois Labourie. So if you have a continuous deformation of tau m of gamma, then every element in this deformation is Anosov. So is a continuous path so of morphism from gamma to SIMR with rho 0 equals the restriction to gamma of this tau m. Then maybe I'll phrase it like this: rho 1 is injective. And rho1 of gamma is what I will call flag Anosov. Okay, so this result doesn't mean anything as long as I do not define what is flag Anosov. So subgroup gamma in SLMR is flag Anosov. So we just say the painful definition. putting it into some orthogonal group, and we will not understand anything, and then I will describe more concretely this definition. So, if the following happens, if 2 of gamma is Anosov, where tau is the action of SLMR on 2, so it's not exactly the space of matrices, but you have to build up some other space, and you have to take some big wedge product of this and to that power. Okay. So I have an orthogonal space where SLM acts. It's the space of matrices with a trace, and I'm taking this external power to. Okay, so but what does it mean concretely? Maybe there is a E here. It means that so gamma is flag Anosov. So there is one equivalent condition just in terms of the growth of the eigenvalue. And if there exists k positive such that for every gamma in gamma and I between 1 and n minus 1, the gap between the i's logarithm and the I plus 1 logarithm of the singular value of gamma is at least the length of gamma. It's bigger than k times the length of gamma minus 1. Okay. But in terms of equivalent maps, this means also the following. So that gamma is hyperbolic. And there exists a map beta from the boundary of the group to the space of complete flags of dimension m. So this is m, sorry. So at beta of eta is n minus 1 tuples of the spaces in Rm, so this is M, that are each is of dimension its subscript, and they are all included in one of them. Okay. So this should be gamma equivalent, continuous, dynamic preserving. There is a transversality that says the following: for every pairs of distinct points and for every I between 1 and m minus 1, the I space of eta sorry, is in direct sum with the n minus I space of eta prime. This is a prime. So beta I of eta and beta n minus 1 and n minus I of eta prime sums to up to. Okay, and there is the last condition. Let me write it here. says that for every I, mu I minus mu I plus 1 goes to plus infinity as gamma goes to infinity in the group. I think next week you will have by Teng Tsang lectures on convex co-compact action in RP2, and by Francois Labourie, a lecture related to Hitchin representation in SIMR. Yeah, but maybe with a different point of view. So now I would like to introduce another subject and take some hints to describe the action of Anosov subgroup on other Frag manifolds and on the symmetric space. And I will restrict the discussion to OPQ. So I will speak of domains of discontinuity and compactification of locally symmetric spaces. So I have, again, OPQ as before. But I will restrict to P bigger than Q. It's not a big restriction. And I want to introduce some space. I will denote F, or maybe sometimes FQ, or FQ, or RP plus Q. So if I need to remember those data, will be the space of Q plane that are isotropic for the quadratic form. So it means the quadratic form that is used to define this OPQ is 0 in restriction to W. Okay, and I want to denote by X, so sometimes XQ, which is the space of Q plane that satisfies the following, so that the so maybe it will be convenient to have a notation for the quadratic form. So I will denote it by B. So the orthogonal group is the orthogonal group of the quadratic form. And such that the restriction of B to W is negative definite. And if you calculate the stabilizer of a point W, it has to stabilize W, but also its orthogonal complement. So stabilizing W means to be in OQ, in restriction to W, and the orthogonal complement gives something in OP. So you can calculate that this is the same that OPQ divided by OP cross OQ, which is the symmetric space. the Riemannian symmetric space of OPQ. I will not use in any meaningful manner the Riemannian properties of this space. Okay. Good. But since I see this space as a subspace of a compact manifold, I get for free a compactification of this symmetric space, which is the set of W in the Grassmannian, such that the restriction of B to W is non-positive. So this contains X, this contains F, and this has a natural OPQ action, and those are two orbits. And in fact, the orbits are easy to understand. So OPQ orbits in X bar are the O subscript I, which is the space of W in X bar, such that the dimension of the kernel of B restricted to W is equal to I. Okay. And basically a consequence of Witt theorem that those are homogeneous on the action of OPQ. So O0 means that this kernel is trivial. So O0 is X, and OQ means that this kernel is everything in W. So it means that W is isotropic and OQ is the orbit F. Okay. So I think this is as far as I need. Okay, so now I need to more notation, which will do the following. I have the limit set of an Anosov representation, which is a part of F1, that is the line in the projective space that are isotropic. And to every subset in F1, I will associate subspaces in F and X bar. So for every lambda in F1, I denote by G of lambda, set of W in F, so isotropic Q-plane, such that there exists a line in lambda which is contained in W. And Y of lambda is the same with F replaced with X bar. So it's the set of W, so that there exists L that is contained in W. So note that by construction, the intersection of those set with X is always 0, because the element in X are Q-plane where the form is non-degenerate and they never contain any isotropic line. Okay. So in this setting, I want to prove these two theorems. So Theorem A will concern the action of Anosov group in F, and Theorem B in X. So if gamma in OPQ is Anosov, then the action of gamma on the complement of G lambda gamma in F is properly discontinuous and co-compact. And the second theorem is almost the same statement, but for the action on X bar. So I take gamma Anosov, and the action of gamma on the complement of Y lambda gamma is properly discontinuous. And co-compact. Oh, sorry. Yes, this is a mistake. So the intersection is empty. Thank you. Thank you. Okay, so what does mean theorem B? It means that gamma mod, so this is a compact set and contains gamma mod X. Precisely because this intersection is empty. So the locally symmetric space associated to this discrete group gamma admits a compactification that is the following, and that is locally modeled on this space X bar. So maybe I would like to remark that when gamma is in OP1, this theorem A and B says a classical fact that the action of gamma on the boundary of the hyperbolic space, when I remove the limit set, is well, okay. So I write this quotient is compact, and in fact the quotient of the compactification, the visual compactification of the hyperbolic plane, when I remove the limit set, maybe it's really better to put parentheses here, is also compact. So now I would like to take some time to explain this result. So I see this result as two different statements about this action. The statement that the action is properly discontinuous, and the statement that the action is co-compact, and I have separate proof for these two statements. And in fact, we'll go the following. We'll prove properly discontinuity in Theorem B, deduce it in Theorem A, and we'll prove co-compactness in Theorem A, and deduce from it co-compactness in Theorem B. So this is what we will do, and I think we have plenty of time to do that. Okay, so this will occupy the rest of my talk, I believe. Okay, so we first show properness in Theorem B. And properness was mentioned a few times already. It means that every compact set is moved out of it by all but finitely many elements. But I will use another characterization of proper action for discrete group. And this is a lemma that is I believe, due to Charles Français, so it's a criterion for proper action. So I have X, a topological space. So maybe I should have a metric space. I think this is safer. I have a group gamma that acts by homeomorphism on X. And we have an equivalent with the fact that the action of gamma on X is properly discontinuous. So if finally the following happens, there is no pairs of sequences so gamma n in gamma and xn in X, such that the sequence xn and gamma n xn converge in X, and the sequence gamma n diverge in gamma. So with xn and gamma n of xn converging in X, and gamma n diverging in gamma. So it is clear that if you have such property, I mean the compact set, which is a union of two neighborhoods of the limit point of these two sequences, have infinitely many elements of the group gamma that bring it to itself. So it's clearly contradicts proper discontinuity, but maybe the remarkable fact is that this is the only obstruction to proper discontinuity in this setting. Okay. So what do we need now is I need to apply this result. So I need to understand what is the dynamical behavior of diverging sequences of in gamma when they act on this complement. Okay, so how do I get a control on diverging sequences in gamma? So I have gamma n, such a sequence. And I will use the Cartan decomposition for gamma n and maybe I will use it narrowly for OPQ. So I would like to be more precise on which quadratic form I'm choosing here. So it's different from the one yesterday. And I want the quadratic form to be, in fact, the most compatible with diagonal matrices. So OPQ is now the set of orthogonal matrices for the form that is anti-diagonal with respect to by block. That's the same matrices JQ1 minus Q, JQ, and JQ is a Q by Q anti-diagonal matrix. Good. And every element gamma n is written as Kn exponential of the diagonal matrix mu1 of gamma, up plus q of gamma, and K prime. So this element belongs to the intersection of O, PQ, and OP plus Q, which is isomorphic to OP cross OQ. Okay, so with OPQ, I choose yesterday, this is easier to see, but it's not very difficult either in this year. And K prime also belong to this. And these diagonal matrices also belong to OPQ, which means that the symmetry I mentioned on the eigenvalues, that mu p plus q is the opposite of mu1 and etc. So what do we know from the diverging character of this sequence? We know that mu1 minus mu2 goes to infinity. And we know also that mu p plus q minus 1 minus mu p plus q also goes to infinity because it is also equal to mu1 minus mu2. Okay. So up to extracting, I can assume that the sequences Kn and K prime m converges. Kn converges to some matrix K, K prime n converges to some matrix K prime. And what is known, so this is from the Anosov property, is that mu1 minus mu2 of gamma n goes to infinity, and mu p plus q minus 1 minus mu p plus q of gamma n is equal to this and also goes to infinity. Okay. And there is a fact that is not very difficult, but not totally easy to see with the definition I gave, that the line L, which is the image of K of the first basis vector. So E1 is the first basis vector of the standard basis of Rp plus Q. So these belong to the limit set of gamma, and as well as the line A prime, which is K prime inverse of R E P plus Q. Good. Okay, so now I would like to understand if I have a sequence that converges in this space, can the sequence gamma n xn converge as well? And I will see that this is not possible. And this is a following lemma. So if a sequence Wn in X bar converges to W, which does not belong to the Y associated to just this one point element. Oh, okay. So I said it already. So E1, EP plus Q is a standard basis of Rp plus Q. Yes. Okay. Okay. So another one, W does not contain a prime. Okay. So it means that the image of W by K prime does not contain this line. This is really what it means. So, K prime W does not contain EP plus Q. Okay. And yes, what happened then? So every accumulation point of the sequence gamma n Wn is contained in the line that is orthogonal to L. So what does it mean to be contained in the line orthogonal to L? So I can pull things back by multiplying by K inverse. So it means that the image of, maybe I'll call it W prime. So prime is not, so W1, it means that K minus 1 of W1 is contained in the span of E1 up to EP plus Q minus 1. So it means that every element in this space have 0 coordinate on the last vectors. But in fact, to analyze this, you just need first to analyze, I mean, we can get rid of the compact factor by changing wn to k prime n wn and w to kw, and multiplying by k prime m on 0. So we just need to understand if a sequence of hyperplane does not convert to an hyperplane, to a Q-plane that does not contain EP plus Q, and if we apply them this sequence of matrices with the last two terms going to plus infinity, then it will kill. I mean, you have to renormalize the vector so that they are contained in Euclidean balls or something like this. And this renormalization and the fact that this difference go to plus infinity will say that for the sequence, the coordinate on the last factor becomes very small and then convert to 0 at infinity. So it's quite a basic calculation, but it is the fundamental calculation in this lemma. So we are not quite there because we wanted, in fact, that this W1 contains L and not to be contained in its orthogonal. But in fact, this is a simple fact or remark, and it is based on the fact that the property that the quadratic form is definite in restriction to W is that W1 is contained in L orthogonal if and only if L contains W1. So this is, in fact, for every L isotropic line and for every W1 in this. Okay, so this first property is, in fact, the fact that L is contained in W1 orthogonal. And you can check that the quadratic form in W1 orthogonal is non-negative this way. Okay. There are different ways of checking this, but every element here is a limit of element in X. And for element in X, I mean, the orthogonal, the line is positive definite, and when you go to the limit, you have something that is non-negative. Okay. So in fact, if you have this proposition and L included in W1 orthogonal, this implies that L is included in the kernel of the quadratic form with so the only isotropic line where the form is of a definite sign, either non-negative or non-positive, as the lines that are contained in the kernel. So, and the kernel in this situation is exactly the intersection W and W orthogonal. Okay. So these remarks say that if I have a line contained here, then it is contained, in fact, in this intersection, so it is contained in L. And vice versa, I mean, the same argument, we say that the line is contained. Okay. So now we have, it's conclude that we have really this property. Okay, so for every, to say it in positive way, for every diverging sequence gamma n for every sequence wn converging in this. Every accumulation point of gamma n xn will converge to a point that is in this subset Y of lambda gamma. Okay, so you can conclude properness in Theorem B. Out of this. So now properness in Theorem A is just a remark when you have a properness in Theorem B. But, let me write it. So is the following thing. I have F, which is a space of isotropic line, which is contained in X bar, and the intersection of F with the set we remove in X bar to have a proper action is precisely the set I call G. So, and the intersection of F with this complement Y is exactly the complement of G of lambda gamma. So, but what is this? This is a subset of X bar minus Y of lambda gamma. And this subset is closed and gamma invariant. So at the quotient, it will give a closed gamma invariant subset of the quotient, which means that I have a closed subset of a compact space, and you deduce out of it co-compact. So the quotient of gamma of F intersected with X bar minus Y is closed and this precisely implies that no, I don't need to do this. Sorry. So this will be useful for co-compactness. So I don't need this, but every compact subset here is also compact in this bigger set. So in this bigger set, it is moved away by all but finitely many elements. So it means that I have properness here. So this is just enough to just properness. So I have so I just said it orally, but I say that this criterion is satisfied for Theorem B. Okay, because what I did prove is that if I have so take sequences gamma n diverging, I take a sequence wn in this open set that convert to some w, and up to extracting, I can I can suppose that I am in the hypothesis of this lemma. So it means that every sequence, every limit of gamma n of wn in X bar is contained in Y subscript L, and L is a point of lambda gamma. So every limit of this sequence does not converge in this space, but converging to something that is out of this space. So it means that I don't have any pairs of sequences that satisfy everything here. And this precisely implies properties. Okay. Good. Okay, so now co-compactness. So to simplify the exposition, I will assume that my group gamma is simple from say a cohomological point of view, but also for a geometrical point of view. So I suppose that it is a group, a co-compact and torsion-free lattice. So I will not put P here, M will be better. Okay. And we'll first assume that P is very big. Okay. So I will be able to say later what do I mean here, but and the last step will be to remove this assumption on P. So I have my subset F, which is the Q-plane, isotropic Q-plane in Rp plus Q. And as you can describe it as a homogeneous space on the action of OP. So it's homogeneous on the action of OP, and stabilizer is really OP minus Q. So you can check this. I mean, what is in general that those frag manifolds are homogeneous on the action of OP cross OQ, but in this particular case, it happened that it is already homogeneous just on the under the action of this subgroup. Okay, but this is SP minus 1 sphere bundle over OP minus 1 minus OP minus Q. No, it's rather the opposite, so it's SP Q minus 1 sphere bundle over OP minus Q plus 1. No, there is no relation. I just want to think that this group as a fundamental group of Riemannian negatively curved manifold of dimension M. Yes, yes, yes. So there is no relation between M and P and Q. No relation between the way I put na gamma as a subgroup of this orthogonal group, and the way gamma was put as a subgroup of OPQ. Okay? Just really to separate action. It's not really a good thing that I chose this, but maybe just okay. So I put isometry of n. N is dimension m, and negatively curve carton Hadamard manifold by 1 of n is 0. I will not need any more. That in fact, what I really need is or use is that the boundary of infinity of gamma is really the boundary of infinity of n, which is in this situation a sphere of dimension n minus 1. Good. Okay, so this is a sphere bundle over something that looks similar. Okay, and this is again a sphere bundle over another bias, and you can go on like this. So what you deduce out of this is the following fact that F is E minus Q minus 2 connected. So, meaning that pi, the homotopy group of F, are 0 for all I between 0 and pi minus Q minus 2. Okay. So it's sphere bundle over sphere bundle over sphere bundle, but as a homotopy group of sphere at least up to the dimension of the sphere, then you can deduce this for the fundamental group. Okay, so the so let's start my argument. And what do we want? We want that the zeros homology group with compact support of this quotient F minus G is R. So what in the Ram homology, what represents this, it's represented by function, locally constant, and that have compact support. So if I have a function that is locally constant and that have compact support, it will mean that the whole space is compact. So this is really what I mean. So maybe I would like to call this space U. And by Poincaré duality, this is the dual of the dimension of this manifold homology group with no compact support. Okay. And now I will introduce N. Okay. So this is isomorphic to so it says that in fact I'm calculating in a way the equivariant homology. Okay. So why is this? You have a map from this space to this one, just forgetting the n factor, and the fiber of this map are contractible. There are this Cartan-Hadamard manifold, so you don't see them in homology. Okay, so the natural map from this gives an isomorphism in homology at every day. And then you can apply Poincaré again. So this is neither dimension of the total manifold chain. So I have now in dimension of n, cohomology, sorry, with compact support of gamma u cross n. So why did we do that? We do that because now we can see this space inside another manifold. So gamma mod u cross n is contained in gamma of f cross n. So this previous quotient, I was not able to consider it as a manifold, but now I add this compact factor, and this is a compact manifold. And the complement of this open subset is really this. Okay, so in this compactly supported homology on this space is in fact the cohomology of this pair. Okay, so I have this group is equal to the where I can put m. This is a dimension of m. The m's cohomology group of the pair gamma f cross n, gamma g cross n. Good. So what gives a long exact sequence for a pair? It gives the following. I have the cohomology of gamma mod g cross n goes to the cohomology of gamma f cross n, goes to the cohomology of the pair, so the gamma f cross n, gamma g cross n. I finished this and I explain. M plus 1 gamma g cross n and m plus 1 last term f cross n. So what is this? You want explanation on this equality? So it's a bit cheated. Okay. So now, what is really this space? Okay, so let me write in range what I didn't want it to write. This is an inductive limit over open set containing what you removed, mod g cross n of as a cohomology of the pair gamma f cross n with respect to O. Okay, cohomology with compact support is really this. And now what you will need to do is to change the rest of the proof I would like to give, but working with the kind of inductive limit of this 5-step sequence, and then see that it works well. But it was okay, but this is so. Can I say something clever? Okay, so I will take maybe 5 minutes just to simplify a little this sequence. So the first thing is that you have a map from this space to the quotient space with fiber that are P minus Q minus 2 connected. So if this number is bigger than M and M plus 1, these two spaces are really just isomorphic to this. So bigger than M plus 1, you get that H of this two integer of F cross N is really the cohomology of this only this space. And I want to understand what is G cross N and how I can see this fibering with really connected fiber. So I would not like to do the same with G cross N, so I need to understand G. And I have a fact that in fact G is a union of things over the boundary of the group, which is the set of things you remove. And the fact is that if L and A prime are transverse, or maybe it's more like this, that two lines are transverse, if and only if the set G of L and G of L prime, so it's just two subsets of the Grassmannian of isotropic plane intersect, does not intersect. So it means that at every point of G, thanks to this property and to the transversality property of the map, I can associate a map, a point in the boundary of a group. So it means that for every, so there exists map from G. I can not write G anymore, I'm sorry. So G lambda gamma to boundary at infinity of the group that is continuous and with fiber isomorphic to the set of Q minus 1 plane in this thing, which is a set of Q minus 1 plane. So it's isomorphic to the set of Q minus 1 plane in R P minus 1 plus Q minus 1. Okay. So this fiber over the boundary of the group with fibers that are really connected. And the same will happen for this product, quotiented by gamma. It will fiber over product quotient by gamma, and I can do the same argument. So it means that this sequence will simplifies, and I will use this tomorrow to deduce really what I wanted, and this is still on the board. So I apologize for going over time, and thank you for your patience.